Alright, today we're going to be working with the graphs of the other trig functions and seeing what they look like and looking at how functions work, how the functions work on a graph. So we'll just start by looking at the features of the graph of the tangent function. One of the key differences here is that the period of the tangent function is going to be pi instead of 2 pi. Part of the reason for that is if you look at our unit circle, if you remember, with tangent being sine over cosine, if you remember that, once we get halfway around the circle, we end up getting the same value on the other half of the circle because the negatives cancel out. So a circle is 2 pi all the way around, so since we only have half the circle, that's pi. Alright, now one of the other aspects of that being sine over cosine. If cosine is 0, I can't do this. Alright, so that means I'm going to have some vertical asymptotes. Alright, so pretty much at 0, cosine is 1, and when we get to pi over 2, cosine is equal to 0. So everywhere that cosine would be equal to 0, so pi over 2 is the first one, and then the next one would be 3 pi over 2, every value of that. So anytime I put an integer value there and add that pi onto pi over 2, I get a vertical asymptote. And the range will be all real numbers. So as I get closer and closer to my pi over 2 on my graph, I get closer and closer to infinity. And if we look at a graph, you'll see that. So here at pi over 2, I've got an asymptote. So I got a vertical asymptote every multiple of pi over 2 on this graph, including the negative. So that would be k being -1 on that last slide. So at the top, I go to positive infinity. At the bottom of each of these, I go to negative infinity. Alright, so you might be thinking, okay, how does that work? Again, with the whole period thing, you can see on each of these, there's a pi between each of these intercepts. There's also a pi value of pi between each of the asymptotes. So that's the other way you can figure out the period from a graph of tangent. Secant and cosecant work a lot like sine and cosine functions. Alright, so on those they have the same period, except here's the problem. Again, secant is going to be 1 over the cosine, and wherever cosine is 0, I'm going to have an asymptote. So we've got vertical asymptotes. The other thing we could say is vertical asymptotes at theta equal to this pi over 2 plus k pi. Cosecant's 1 over the sine. So we have pretty much the same idea with the asymptotes, except they've been shifted because sine and cosine are pi over 2 apart from each other. So that's where there's a difference between these two domains. And then the other thing, the ranges are going to go from negative infinity to -1, and then it's a union in this case of +1 to positive infinity. And let's look at the graph of that so you can kind of understand that. So on this graph, this top part is the secant, and I included the cosine function as a dashed line. Alright, so that's the secant of theta, and the bottom was the cosine of theta. Because I wanted you to see, so wherever cosine is 0 is where I have an asymptote. So everywhere that cosine is 0 is where I have an asymptote. Alright, and when we look at some graphs, or look at graphing this function, we'll start by doing the cosine first to get started so you can see where these values occur. And while they don't necessarily have an amplitude on the secant, when I look at this, it's pretty much the same as what it works with cosine. So if I put a 2 in front of the cosine, if I put a 2 in front of the secant, it'll just spread apart how far apart these peaks are and where these dips are. Alright, and if we look at cosecant, same thing except it's goes with the sine function. Alright, so instead of touching the 0, I have an asymptote there. I have an asymptote every value of pi. Now you might be thinking, but Mr. Harbison, you said the period was 2 pi. So technically this is 2 pi, but you have an asymptote right in the middle of that 2 pi. So if you break it down, you've got 2 pieces here that are in that period because they're the 2 pieces that are with the sine function in that period. And we've also got the cotangent function. So as you would expect, the cotangent function has the same period as the tangent function, but the domain is a little different because instead of cosine on the bottom, I now have sine on the bottom. So the cotangent is sine over, or cosine over sine. So the domain is going to be where sine is equal to 0. Sine is equal to 0 at all values of pi. So 0, pi, 2 pi, 3 pi, 4 pi, so on and so forth. So that's where k comes in. And again, just like tangent, my range is from negative infinity to positive infinity. So it looks a lot like the tangent function, except for I've got different asymptotes. So 0 is an asymptote in this case, pi is an asymptote, 2 pi is an asymptote, and my function comes down from infinity in one period and goes to negative infinity in one period. So let's look at a few of these. Alright, so we're asked to find a period in the horizontal shift for this function, f of x equals 2 tangent, and then we've got the quantity 4x minus 32. So just like before, I would go ahead and start by factoring this out. So factor this. Alright, we can still find the period without doing that, but let's just go ahead and factor it. So I got 2 tangent, and if I factor that, I got 4, and then I got x minus 8. So just like before, we're going to use this number for the period. This is not the period. This is more of our b value like we had before. I'm just going to keep that notation the same so I don't confuse you. So in this case, though, I'm going to do pi divided by that for the period. Because before, we had to do 2 pi divided by that number. This time it's just pi because the period is different. So the period for tangent is different, so we have to use pi over 4. So that's our period. I don't have to simplify that out anymore. Since I factored this out, I'm going right 8 for my horizontal shift. Alright, so my horizontal shift is right 8. My period is pi over 4. Again, this one's already factored out, so when we look for the horizontal shift, it's nice and easy. It's got a horizontal shift of left 1 unit. And this works a lot like cosine because it's secant. So we've got to remember, since it's like cosine, I'm going to do my period is 2 pi divided by pi over 4. So when I do that, I get 2 pi times 4 over pi, which is 8. So again, these look just like what we did before, except with different functions. So you read the information pretty much the same way. If it's tangent or cotangent, you got to remember the period is a little different. It's pi instead of 2 pi. So sketch a graph of 2 secant pi over 4 and then the x plus 1. So for this, let's go ahead and do a few things like we started off before with cosine. Since secant is related to cosine, we're going to use our ideas for cosine. If we had cosecant, we would use our sine function. So we got to figure out a few things. Number one, the period. So our period here is equal to pi, 2 pi divided by pi over 4. So again, just like last time, that equals 8. So this is the exact same problem that we just had. Alright, my horizontal shift is 1 left. Now, this 2 kind of works like the amplitude. So we could start by doing a cosine function, and then once we had our cosine function, we would have pretty much what we had with the other graphs. So I'm going to start with a cosine function. So I'm going to skip over, this is 1, -1, -2, -3, -4, -5, -6, -7. This is 1, 2, 3, 4. And then I'm going to go up by the same interval. So a couple differences, but it's going to work out a lot like we did before. So my normal cosine would be at, a peak would be at 2, and then I go over here 1. Alright, and then when I get to 0, normally I would be at 1. Normally at 1, so since this is stretched out with the other, I'm going to be down here, and then I come back up at 5. 1, 2, 3, 4, 5. And I got at 3, I'm down at -2. Alright, so this would be my normal cosine function. So I'm doing this first so that when we see it, so I need to see where these zeros are, because when I see where these zeros are, I can do something. So for my cosecant, I'm going to have asymptotes right here. I'm going to be right here. I'm going to be right here. So these are my asymptotes. Now, how can we figure those asymptotes out from the original function? We had that pi over 2 plus k pi for our asymptotes. Alright, so those are our vertical asymptotes. And what I want you to notice, these are 4 apart. So our period is 8, these are 4 apart, and really they're all shifted because of this as well. So what's nice about this is our maximums and our minimums correspond to each other when we actually graph it. So if we do it, I did a terrible job with that one. It needs to be over here like this. So the red graph is actually my cosecant graph. So you're like, well, we can do this without doing all that, and yes, you can. Again, and the purpose of this one is just to show you kind of how that works so that you can get a good start on it. I'm sure we'll have to talk about it a little bit more when you go to sketch some of them. So when we're looking at these functions, we can do some very similar things. Number one, we want to look at what's on my y-axis. Is the y-axis an asymptote or not? In this case, the y-axis is not an asymptote, so this would be a secant function. Alright, so this would be a secant function. I don't have any shift here, left or right, so that helps. And just like before, we can count our period by doing this. I'm going to count from 2 to -2. That's 4. Alright, same thing if I do 0 to 4, that's 4. So that's my period. If I want to do half my period, I can go from top to bottom, and then that would be half my period. But again, my my function is going to have the same kind of period as we did before. 2 pi divided by that number 4 will give us our value in our function. Alright, so that's pi over 2. Another thing that we need to notice, alright, I'll leave that 4 there. From this maximum to that minimum is how tall? That's 4. So that spacing there can help us find our amplitude. Now our midline, again, is our vertical shift, is right in the middle of this. So it's not really called a midline now, but that's our shift. So our vertical shift is +2. And when I write my final function, f of x, I take half of that 4. So 4 divided by 2. It's kind of still the same thing as amplitude. So that's going to be 2. And then I've got secant of pi over 2x plus 2. Alright, so it's very similar to what we did before. It just has secant. The graph doesn't quite look the same because it's not cosine. So again, this one's very similar to the last one. We're trying to find a formula for this function. And we've got to look at a couple things. Number one, I want you to notice that an asymptote is right here on the y-axis. So that means that it's going to be cosecant. Alright, the other thing, we go from our max to the minimum, and in this case I'm going from -3 up to 1. That would be a distance of 4. So my amplitude, or my a value, is 2, just like we did before. The other thing we need is our period. So in this case I'm going from -6 to 2, that's an 8, and that means my period is 8. And just like before, we're going to do 2 pi divided by 8, since this is just like sine, and that gives me pi over 4. So that means my function is going to be 2, and I've got cosecant of pi over 4x, and then in the middle of these, kind of the midpoint line, this has been shifted down 1. Now last time we had a few identities with cosine and sine with negative angles, and we get similar things here. So the tangent of a negative angle is just the negative tangent of the angle. Cotangent of a negative angle is the negative cotangent of the angle. Secant of the negative angle is just the secant of the angle. And the cosecant has the negative out front. So you might be like, why is this one the only one like that? Just remember, before with cosine we had a very similar relationship, and with sine we had just like the other ones with the negative out front. So these three all have a sine in them. That's why they have the negative out front. This one is a cosine, so it doesn't have the negative out front. And we're going to use those a few times. Alright, so if tangent of x is -1.5, we need to find tangent of negative x. So on the last slide I had tangent of negative x, which is the negative tangent of x. So that means I need to take a -1.5, which means I have 1.5. Down here, cosecant of negative x is equal to the negative cosecant of x. So again, all of them work that way except for cosine and secant. So just remember, cosine and secant don't have the negative out front, the other ones do. These are all on your reference sheet. So in this case I'm going to do -5, which is 5. And there are a couple times where you can use those to simplify an expression, kind of like we did before with into a single trig function. So the first thing we need to do with this expression I got the cotangent of negative x, the cosine of negative x, and the sine of negative x. So we need to get that negative out of the parentheses inside. So negative cotangent of x is the same as cotangent of negative x. Cosine of negative x is cosine of x. And sine of negative x is minus the sine of x. Then we can do our changing cotangent into negative cosine of x over cosine of x, or sine of x, my bad. Said the wrong thing there. Times the cosine of x, and then that's still minus the sine of x. And what we have here is cosine times cosine, so that's negative cosine squared of x over sine of x. And I need to combine this with a fraction, so I need to make it into a fraction. That's sine squared of x over sine of x. And that gives me cosine squared of x plus sine squared of x if I factor out that negative over the sine of x. And that gives me negative 1 over the sine of x, which is negative cosecant of x. So again, we're just using the other trig functions here and doing some work with these negative angle identities. So have fun with this. Good luck.